Hi all. Y'all hear me?
Mhm.
Yeah. Cool. All right. All right. We're just waiting for people to show up. Give it a minute. What do we got? 5, 6, 7. We got 7. All right. Let's give it 2 more minutes and we'll get started.
Professor, do you know what's going to happen with our midterm?
Yes. I don't think we're having a second midterm. But I'll say more about that when there's more people.
Right. If we don't have a second midterm, can we at least still have like the review session so that we can
We can definitely have a day of review. Sure. Yeah.
Cool.
Yeah.
Thank you.
How many more class days do we have? Let me count. Let's see. I have 1, 2, 3. It's like we have 10 more class days, including today. All right, we're getting there. Let's see. 1, 2, 3. We got 9. I'll start when 1 or 2 more show up. Let's give it another minute or 2. One more minute. All right. All right, let's get started. How many are we at here? Oh yeah, we've got almost everybody. 6, 7, 8, 9, 10. 10. Okay, great. If you all wouldn't mind putting your video on, that'd be great, but it's certainly not going to require it. Just nice to see all your faces. So you don't have to. Couple of quick announcements. We've been having a whole lot of debate at Pitzer over whether or not all classes should be pass-fail for this semester. Let me explain to you some of the issues in case that hasn't kind of leaked into all your consciousnesses yet, and then I'll tell you what happened at the faculty meeting and then where we're at. The thinking is that this is a serious equity issue. I don't know where you all are at or what's happening in your own lives, but we have reports of a lot of students who are couch surfing because they don't have a stable home life to go to, or they've gone home and they're sharing a room with a sibling, and so they're just not in a position where they can physically participate to their fullest extent with the same level of concentration as other students. Or they're in a house with one computer for everyone in the house, or two computers for everyone in the house, or they're in a radically different time zone, so they don't have live access to their instructors because whenever they're awake, their instructors are asleep, or the list goes on and on and on and on for all of the challenges various students are facing at this time, and why there's serious inequalities going on, and everybody's facing different levels of challenge, right? So I don't know what's happening in your lives. Maybe you're fine. Maybe you have your own room and a place to go to, and your parents leave you alone, or maybe not. But there's a lot of issues of just what's fair, what's the right thing to do. Can we really grade everyone on the same scale, given that everyone's not in the same environment by any means? So the thinking is that everyone should go to a pass-fail system. That way we kind of level the playing field. There's debate over, some people have proposed an automatic pass for all students. I think that got shot down. Normally pass-fail means you have to get a C or better to pass. So in some sense, you're worse off if you get a D under the pass-fail system than under the letter grade system. Technically, a D is a passing grade, but in a pass-fail course, you will fail the course if you get a D. So there's controversy over that. As a mathematician, my primary responsibility for most math classes is to make sure you're ready for the next class. And I would be very hesitant passing you in a class if I didn't feel like you're ready for the next class. And usually prerequisite classes, they say C or better in the previous class, not just pass in the previous class, but C or better. So if we go to pass-fail as a college, I will certainly support us preserving C or better being passing, just because from my perspective, that's the right thing to do. But I know other people feel differently. The Student Senate has met at Pitzer, and the students have recommended a universal A system. So students really don't have to worry about how this is going to affect their GPA. If everybody gets an A, then everybody's happy, essentially. I don't even think that was considered by the faculty, to be honest, although some colleges may be going that direction. And I think where we're headed is more toward just pass-fail for all courses. Lots and lots of colleges across the country are doing this. The most prominent one that's making a lot of headlines is Harvard. Harvard's already gone to a universal pass-fail system. With no exceptions, as far as I know, they are not allowing students to appeal to have a letter grade. Some of the concerns students have raised is that I know there's a lot of students who are thinking about the health sciences and nursing schools, medical schools in particular, are kind of notorious for only accepting letter graded classes, not accepting pass fail classes for medical schools. Other employers, students may be worried other employers may also only look at letter graded courses. We've now talked to a lot of people, including medical schools, and I think everyone is recognizing that spring 2020 is a historically different time period, and everyone seems to recognize that that pass fail is probably the right thing to do at this point. So um, the college voted on Thursday to go to a default of pass fail for all Pitzer students, not for all Pitzer classes, which I thought was very strange. And I think they're reconsidering that. I think the Pitzer policy is going to change probably multiple times between now and the end of the semester. The first thing that got passed was last Thursday. Well, the first thing that got passed was at the dean's level when this whole pandemic hit. The dean said any student who wants to go pass fail can. That's up to you guys. Also, any instructor can switch anybody to pass fail that they want. So has been left up to the instructor's discretion and the student's request from the beginning. What changed on Thursday is the college went to a default of pass fail for all Pitzer students. So if you are a Pitzer student, from this point forward, I think you've been officially switched to pass fail. They're not calling it pass fail though, because some students have objected saying, hey, pass fail in spring 2020 should look somehow different on a transcript than pass fail some other semester. So they've come up with a new naming system, which is called something like, I forget what it is. It's going to look different on your transcript. It's like emergency credit. I think that's what it is. EC or something, ERC, emergency credit / emergency no credit or something like that to really emphasize this is an emergency situation. So we are moving to that system for all Pitzer students. I teach classes that are a lot more mixed than many of my Pitzer colleagues. My CS5 class has 50 students. I think only about 15 of those are from Pitzer. And I really don't like the idea that some of my students are going to be defaulted into pass fail while other ones are not. So I think what I'm going to do is just switch all my classes to pass fail. Also because I agree that given what's going on right now with the world, that's the right thing to do. If you have serious problems with that, if there is some reason why you think you really, really need to get a letter grade for this course, other than just, you want it to help your GPA, hey, you've been running an A so far, you don't want to be deprived of that A. Those requests I'm not going to look so favorably on, but if you have some other reason why you want a letter grade that I'm not thinking about, we can have a conversation. You can email me. We can talk about that. There's an equity issue even asking for requests for who wants a letter grade and who doesn't, because students who are in a position of privilege, who are in situations where they can succeed, they'll request a letter grade. Students who are not won't request a letter grade, and then you create this two-tier system between the students getting letter grades and the students who aren't. And so there's a lot to think about. There's a lot of issues here of fairness and equity, and we're all struggling with this. All the faculty are thinking about what's the right thing to do. I know these conversations are happening at all 5 colleges. I know I have colleagues at both Pomona and Harvey Mudd who I've talked to who have said they're thinking about it too. And I'm fairly certain Harvey Mudd at least is leaning toward also going toward a universal pass-fail system as well. So with that said, I'm going to switch you all to pass-fail. Again, if there's some really compelling reason why you think you should be getting a letter grade in this course, you can talk to me. And I could presumably switch you back for now unless the college decides that we're going to move to a system where there will be no exceptions. That would happen at the college level. And it's possible that will happen, just to warn you. Other things is, given that I am switching us all to pass fail, I think that, well, there's other things going on, which is that one of the reasons to go to pass fail is that a lot of people are facing particular challenges and particular stresses. Not everyone is in the same boat, obviously, but some people are having real problems. You know, some people have this virus, or their parents have this virus, or a close family member. I mean, there's a whole lot going on right now. So um, there's also been a lot of talk about trying to relieve as much pressure on the students as possible, reduce the amount of stress you all are experiencing. And one of the biggest sources of anxiety and stress is testing. So um, I am still going to give a final exam in this class. I haven't quite figured out how to do that on this new electronic world we're in. But I think we're not going to have a second midterm. So we'll just keep going with the homeworks. There's going to be a lot of recommended problems out of the book now. As we go further, it's going to be harder and harder for me to find web work problems. There's still some. We'll still have a smattering of web work problems. We'll have more suggested book problems. And there will be some kind of final exam that'll be taken online. But I don't think we have to worry about the second midterm that was originally planned. And as far as grading scale, again, I said C or better to pass, but mostly I'm going to look at whether or not you've just been attending, been doing the work, been doing, you know, the web work problems, you've been at least making an effort. I will certainly look at the final exam and see how you did, see if that shows any evidence that really what I'm looking for, again, is that you are ready for the next class. If you take another class for which differential equations is a prerequisite, I'm going to be looking to see that you're ready for that. And if I don't care so much if you get an A or a B, as long as I think that you'll do okay in a class that requires this material. So some of that will really be an opinion-based question, but I'll try to be as objective as possible with that. All right, I've just been babbling about this for 10 minutes. Questions? Do you guys have any questions about this? I don't have my chat window up. I don't know if anybody's chatted. No, nobody's chatted. Issues, you could talk to me privately during office hours. You could email me if you have issues with this, or if you just have general questions now about how this is all going to work. Please just turn on your mic and yell it out, or type it into the chat window.
So I just have a question about, like, so you're moving all of us to a pass-fail system. So
Yeah.
does that mean like you'd be more reluctant to having us get letter grades?
Yes. Yes. I think
Okay.
I'm definitely been convinced from all the debates I've heard and from everything that I've heard that it's not fair to have some students request letter grades and some students request and be on pass fail, because the ones who request letter grades are the ones who are in more advantaged situations. And we want to try to be fair to everybody. You know, with that said, again, I'll repeat that maybe some of you have compelling reasons why you need a letter grade, and I will certainly listen to those requests. So I don't want to make any kind of universal proclamations, like no exceptions at all. I'm not saying that right now. The college may eventually say that, but I'm not saying that. But I will say I'll be more hesitant to move you toward a letter grade just because you requested it.
Professor.
Other questions? Does everybody understand my rationale for that? The reasons? It's not my rationale. I mean, it's just I've kind of been convinced that that's the right thing to do. Yeah, Zhao, you had a question?
So the weighting now will be based on the first midterm, the homeworks, and the exam will that be like 33% each, or more weight towards the?
Again, I mean, I'm really going to be looking at whether or not I think you're ready for the next class. I should be able to tell that entirely from the final exam, but I don't want to put a lot of pressure on you for the final. And if you bomb the final because you were too stressed or in an environment where you couldn't do it, then I'm not going to say it's 100% the final. But If you do well on the final, I don't have a problem passing the class. If you don't do well on the final, I'm going to look at the other stuff. That makes sense. I will try. I know that sort of vagueness is not helpful for you and can only increase your stress level. And part of the reason I'm being so vague is because I don't have an answer, actually. I will try to come up with some definite grading rubric so you know what percent the final is worth and that sort of thing. I just don't have those answers right now because I haven't. This is all new to me. I haven't really thought this through.
No problem.
Yeah. It will probably be something like, if you pass the final, then you pass the class. If you don't pass the final, then I'll look at the other stuff with some weighting.
Okay. Got it. Thank you.
Sure. Other questions?
Professor, what were you saying about like if we're thinking about like graduate school in the future, do you think that like the semester will be like viewed like if we like have everything as like PNCs and stuff?
Yeah. I think that graduate schools are fairly going to use universally. We've talked to a lot of graduate schools. From everything everyone else has told us, everyone's going to look at this semester and recognize something weird was going on and passes, all letter grades up to this point, and then all pass fails in this semester. Everyone's going to understand what that meant, why that was.
Mm-hmm.
And it's not going to reflect poorly on anybody.
But I mean, like suppose differential equations is like really important to like someone's like you want like your grade in diff PQ to like be a thing that you have on your transcript.
Yeah.
Is that like maybe rationale for opting back towards grades, or
You know what I would do in that situation? Number one, you can if you're going to graduate school, you'll have an opportunity to say something in the letter, whatever essay you write for the graduate program. If you do well in this class, I'm happy to write you a letter of recommendation. And then I could say in the letter, hey, we were pass-fail this semester because of the pandemic, but this guy did great in my differential equations class, and you should all know that he was a great student. Okay, I'm happy to say that for any of you who do great. I'm not going to lie, but if you do well, then I'm happy to say that, put that in writing.
Thank you.
Other questions? All right. Well, let's put that all behind us now and try to concentrate on learning as much as we can, getting through some differential equations and learning some stuff. I just counted a minute ago. We have 10 class days left, including today. At the very least, I'll tell you where we are in the book. We're going to finish chapter 3 today. We're going to skip chapter 4 temporarily. We will come back to it and kind of hit bits and pieces of it, kind of in the rearview mirror. We're going to go straight from chapter 3 to chapter 5. We'll spend 2 or 3 class days on the first couple of sections of chapter 5. The first section of chapter 5, actually, I think the first 2 sections of chapter 5, we may spend 2 class days on each of those sections. So a good chunk of the time we have left will be in just the beginning of chapter 5. We will cover all of chapter 5. So there's 6 sections total in chapter 5. And again, we only have 10 class days left. So a lot of the time we have left will be on today, finishing chapter 3, then all of chapter 5. And then we'll have a couple of class days left where I'm going to kind of just pick and choose the topics I think are the most interesting, the most fun in the remainder of the book, and we can jump around. I think chapter 8 is just fun. There's a lot of interesting, fun stuff in chapter 8. If any of you are engineering, pre-engineering, chapter 6 is important. So maybe I'll do a survey of the class and see where you all are headed in your life. And there are some interesting things in chapter 4 that we'll jump back to as well. Okay, so we'll kind of jump around after chapter 5. All right, but let's finish up 3.8. 3.8 is the last section in chapter 3. And the idea here is to just take everything we've done in 2 dimensions. So up till now, we've had systems of differential equations where we've had 2 equations and 2 unknowns. And we want to think about what happens when we bump that up into n dimensions. That's easiest to think about if n is 3. So going from just 2 dimensions to 3 dimensions. The nice thing about 3 dimensions is that we can still visualize what's going on because we can visualize 3 dimensions. We can't visualize 4 or 5 dimensions. But, and the book doesn't talk about higher dimensions very much. I'm going to say a lot of things about higher dimensions. And the point is that once you know how to go from 2 dimensions to 3 dimensions, nothing changes. You can go from to 4 to 5 to 6. It's all the same. And actually, in some sense, there's nothing new going from 2 to 3. 2 dimensions is the hard case. There's a lot of new stuff going from 1 dimension to 2 dimensions. Going from 2 to 3, there's nothing new. Just the pictures are going to change. So I'll just remind you, in 1 dimension, that's where we started, 1-dimensional linear systems, the phase, we had a phase line, not a phase plane. The phase line always had an equilibrium point in the center, right at 0 on the real axis. And everything pointed toward that or away from that, or you could have a node where things point toward away, right? So we had saddle sinks and nodes, sorry, sources, sinks, and nodes. We do not have saddle behavior or any other complex behavior we've seen. In 2 dimensions, we saw a lot of new behavior. We saw not just sinks and sources, but spiral sinks and spiral sources. We saw center tangencies, things going around the origin. We saw lines of 0 equilibrium points where you have things going to those lines. We saw saddles. Saddles were new in 2 dimensions. Sorry. So a lot of new stuff happened when we went from 1 dimension to 2 dimensions. Nothing new is going to happen from 2 to 3 or 3 to 4. Okay, we've done everything we're going to do. You just have to understand how the algebra changes and how the pictures change, but the types of phenomena we're going to see are exactly the same. Okay? Nothing new. And that what really there's a very deep reason for that, and the reason is called the fundamental theorem of algebra. Let me get my iPad screen up for a second here. And I'll start writing stuff down. Let's see, cable. All right, hopefully you all are seeing my iPad screen right now. Oh, no, you're not. All right, awesome. You should be seeing it now. Okay, the fundamental theorem of algebra. Does anybody know what it is?
Isn't it like, it has to do with like the polynomials with the
Yeah.
degrees that
Yeah.
equates to the number of roots you have?
Yeah, that's exactly what it is. Yeah. Fundamental theorem of algebra says that if you have a degree n polynomial, it has exactly n roots. Okay, that may not be the theorem you learned. You may have learned the theorem that says it has at most n roots. Okay, but it doesn't have most n roots. It has exactly n roots, as long as you allow a couple things. So it really is exactly, but you've got to allow a few things. You have to allow for repeated roots. So you can have the same root appear 3 times, right? And that counts as 3 things toward the n total that you're supposed to see. But the other important thing is that you have to allow complex roots. And in a high school calculus class, when you learn the fundamental theorem of calculus, the fundamental theorem of algebra, not calculus, you typically aren't looking at complex roots. So they say, hey, you have at most n roots. You may not have n roots because some of them were actually complex. And so you didn't even think about those in high school necessarily. Okay, but if you allow complex numbers, you find several real roots and typically several complex roots. And the complex roots always correspond to complex conjugates. So they always come in pairs. A plus or minus bi. So if you find 2 plus 3i as one root, then 2 minus 3i will be another root. Okay, so things are paired up. So now what does this have to do with differential equations? When we're solving a system of differential equations, if we have a system of n differential equations with n variables, change color back, n differential equations, means remember the first step was to find the eigenvalues. The eigenvalues means you write down the characteristic polynomial. And if you have n differential equations, then you get a polynomial of degree n, okay? And that polynomial of degree n will have n roots by the fundamental theorem of algebra. And some of those roots will come in pairs corresponding to these complex conjugate pairs, okay? Some of these will be complex, all right? There'll also be n eigenvalues and we've seen even in the complex case, the eigenvalues, not eigenvalues, eigenvectors. And even in the complex case, the eigenvectors have come in pairs. They have a real and imaginary part. So these will always be real if you take the real and imaginary part of those complex eigenvectors. All right, now what does this mean? So the eigenvectors, again, tell you the direction on which the eigenvalues are moving things toward or away from the origin. So let's say I'm in 3 dimensions, x, y, z. If I find 3 real, let's just look at the case we have 3 real eigenvalues. All right, and let's just make up some numbers here, 2, 3, and -1. Okay, all right, so what does that mean? So 3 real eigenvalues means I also have 3 real eigenvectors. So let me circle these, let me color code these. Since I have these colors, I might as well use them. So we have an eigenspace, a whole line of eigenvectors that corresponds to lambda equals 2. So there'll be this whole line in 3 dimensions corresponding to lambda equals 2. And there'll be a whole line in 3 dimensions corresponding to lambda equals 3. Okay. On the red line, where lambda equals 2, things are going to move away from the origin. On the green line, where lambda equals 3, things also move away from the origin. And on the blue line, there'll be some third line in space. This blue line, lambda equals -1, that means things move toward the origin along that line. And then everything else moves along curves, typically does not move along straight lines. And one of the things you can do is you can look at subplanes to figure out what's happening here. So let's just look at the plane spanned by the red line and the green line here. So there's this plane in 3 dimensions. Okay. The blue line's going right through that plane, and the red and green lines are in that plane. Everybody see that? Just nod if you're with me. Can you see my iPad screen? Am I just talking? You're not seeing anything? You're good? All right, good. All right, so in that red-green plane, generally things look like, I wish I had purple. Maybe I do have purple. Hold on. What's a good color? Yeah, there's purple. Red and green make purple. No? Red and blue make purple. What do red and green make? Orange?
They're complementary colors, so I think they would make like brown.
Brown? All right. I got brown. Okay, cool. All right, in the red-green plane, things are going to move away from the origin. Not if you just think about that plane. Let's take that plane away from. Let's just for a minute take this plane and lift it out of the picture and look at it straight on. And in that plane, we see a green axis where things are moving away from the origin, and we see a red axis where things are moving away from the origin. And this is now just like a two-dimensional system. Things, when you have a source like this with two different eigenvalues, 2 and 3, things generally move, let's see, let's pull up that brown. Things generally move along parabolas. In that plane, right? So if we're just stuck in that plane, then things are going to move along these parabolas. Away from the origin. So things just look just like they do in 2 dimensions. That's just happening in a hyperplane, a plane through the origin in 3 dimensions. Okay, it's just like the picture that we would see in a plane with 2 real eigenvalues, both positive. Okay. If we look at instead, let's look at the red-blue plane. So I need a plane here. I know the picture is going to get really confusing. In the red-blue plane, if I look at that straight on, we've got, let's see, red in one direction, where things move away from the origin, blue in another direction, where things are moving toward the origin, and then off that, okay, now I know red and blue make purple, right? So let's see, we need purple. Here's purple. Off that, things are going to move and along these hyperbolas, these hyperbolic curves. So that's what's happening in this plane here in 3 dimensions. Things are moving in 3 dimensions away from the origin. Along these saddle curves. Okay, so that's also happening. I'm not going to draw it. Maybe I will draw it. At the risk of making a really unreadable picture, there's also this plane spanned by the blue and green curve. And in that plane, things also move along saddle lines. What color what's blue and green? What does that make?
Turquoise.
Turquoise? Okay, I like turquoise. Turquoise. Oh, there's a nice turquoise, yes. In that plane, things are also moving along saddle curves. I hope, despite how messy this picture has gotten, you're getting some sense of what's going on. There's this line right here. Let me now sort of emphasize it. There's this blue line. It's very important. And then there's this black plane containing the red and green stuff. So where was that? That was this original plane. Everybody see that? There's the blue line and the black plane. On the blue line, things are moving toward the origin. And on the black plane, everything's moving away from the origin. And if I pick a point that's just off the blue line, it's going to follow that blue line toward the origin until it gets close to that black plane, and then it's going to shoot away from the origin. Right? Things near that axis. Sorry, I just saw that there were some shots coming through. Okay, good. Everybody good now? Can everybody see the iPad screen? Yeah, good. All right. On that blue line, everything's moving toward the origin. So near that blue line, things are going to move toward the origin. And then as soon as they get near that black bean, they get shot away from the origin. Is that totally confusing, or is that you kind of getting the hang of that? I know the picture's gotten to be a mess. Maybe I'll draw that picture one more time. We've got this black plane where things are moving away from the origin. I'm just going to do it all in black now. Things are moving away from the origin in two directions, and they're moving along parabolas in two directions. And then we have this other direction that's somehow away from the black plane, where things move toward the origin. And then everywhere else, things kind of follow parallel to one line until they get near the plane, and then they go away, like sort of like satellites. This is considered a three-dimensional saddle. Saddle just means in some direction, in at least one direction you're going toward the origin, and at least one direction you're going away from the origin. That's all saddle means. So there's at least one greater than or equal to one direction toward the origin, and at least one direction away from the origin. Sorry about my handwriting. It's particularly difficult to write on legibly on an iPad. Is this picture clear at least? Yeah, good, okay. All right. Now we can have any kind of behavior here. So let's look at a couple of other examples. Let's do 3 real eigenvalues where they're all negative. So if we have 3 real eigenvalues where they're all negative, it means we have these 3 axes where things move toward the origin. And in some third direction here now, things are moving toward the origin. And then everything else also moves toward the origin, but it all just follows some curve. And the concavity of that curve just depends on kind of the relative magnitudes of those 3 eigenvalues. We're not going to be drawing the least bit accurate pictures here. So in 2 dimensions, we spent some time talking about whether or not the curve is going toward the axis with the smaller eigenvalue or bigger eigenvalue. Here, the only thing I want you to know is kind of more holistic information, that everything moves toward the origin, and it's going to do so along some curve. I hope that's obvious. I hope it's obvious. Obvious-ish, right? The point is nothing's different, right? We have these lines where we have certain behavior depending on the eigenvalues, and that gives us curves when we're off those lines. Same thing happens in 3 dimensions and 2 dimensions. Okay. All right, let's talk a little bit more. What if we have, wait, going back. I hope it's obvious what the name for this kind of equilibrium point should be. This would be a sink. So sink just means everything's moving toward the origin. And we're not going to make so much of a distinction now between spiral sinks and spiral sources, and we'll see something called like a spiral, you could call it like a spiral saddle in a minute. Right now, we're mostly just going to classify things into sink, source, or saddle. Although there is certainly other behavior that we'll see. Suresh, you had a question?
So as you go into higher dimensions, is it like more and more likely to get saddle points?
Yeah.
Because like, okay.
Yeah. Just think about you just think about it from a probabilistic standpoint. Imagine every eigenvalue. Let's say you have 100 real eigenvalues. Let's say they're all real. Each one is either positive or negative. So the chance that they're all positive is 2 to the 100th. Um,
Mm.
or sorry, it's 1 out of 2 to the 100th, right? You've got 2 possibilities for 100 things. They have to, if they're all positive, that means you've picked one specific possibility for all 100 things, right? So 1 out of 2 to the 100th is the probability that they're all positive. If they were all just picked randomly. Okay. Now, of course, in a specific physical situation, something about the physics of the situation may tell you that, you know, you definitely are dealing with a sink, right? Maybe, for example, here's an extreme version of a sink. Maybe you're modeling the gravitational fields of a black hole when things are literally a sink in 3 dimensions, right? Everything moves towards a black hole, right? In which case you wouldn't expect a saddle of any sort for gravitational vector fields. Okay. Or maybe you've got, you know, electric charges and you have a positive charge somewhere. Everything's going to move away from that positive charge, so you've got a source. Other positive things will move away from that positive charge, right? So, you know, there may be physical reasons why you have a sink and a source, but as you're pointing out, if you're just picking random eigenvalues, yeah, it's unlikely it'll be a sink or a source. Another situation you can have is a pair of complex eigenvalues. So again, a pair of complex eigenvalues, and we'll work through an example like this in a minute. I'll just do the example straight out of the book. So you'll see how this works algebraically. But before we work through the algebra, I want you to just see what happens geometrically, what the pictures are. So if you have a pair of complex eigenvalues, then they'll correspond to complex eigenvectors. So let's just say we had let's see, 2 plus or minus 3i. Okay, now that'll correspond to an eigenvector. Let's say just 2 plus 3i might correspond to the eigenvalue vector 1, 0, 1 plus I times minus 1, minus 1, 0. I'm just making something up right now. Okay, so if you remember what we did when we were working with complex eigenvalues, the way we solve those systems is we just took one of the 2 eigenvalues. We found the eigenvector that it corresponds to. And then we took the real and imaginary part of that eigenvector. And then we looked at all possible combinations of those. And that gave us the entire space of all solutions to the original differential equation. We never actually had to look at the eigenvector corresponding to the other eigenvalue. And the same thing is true now. Well, a pair of complex eigenvalues will give us these 2 eigenvectors, and those 2 eigenvectors will correspond to 2 lines in 3 dimensions. Oops, I need a third axis. Okay. So we'll have these 2 lines in 3 dimensions, these 2 red lines. Okay. Now again, if this is a 3-dimensional system, then there will be 3 roots for the characteristic polynomial. If one of the roots is complex, then another root has to be complex, right? So we've accounted for 2 of the 3. The third root can't also be complex, because then it would have to pair with another complex conjugate. So the third root has to be real in this case, right? So we know for sure there'll be another root, which will just be a real number. Let's call it, ooh, I should color code this. Need another color, green. Can you all see green? Doesn't show up very well on my screen. Can you see that green?
Yes.
Sorry. There's a weird animal sound in the room that I'm working in. I think it's my dog, but I'm not totally sure it's my dog. So it didn't actually sound like it's my dog. I'm just gonna keep going, assuming that's not a monster. Okay. Let's give this one a -2. So we have a negative real eigenvalue. That's going to correspond to some line in space where things are going toward the origin. Okay. And then we also have this plane, this red plane. And what's happening on that red plane? If you have eigenvalues of 2 plus or minus 3i, just by looking at that, if this were a 2-dimensional system, you should know what that is, how you would describe that picture. I'll give you a hint. The real part is 2, and it's complex. Really? Nobody remembers? Somebody's got to remember. Just put it in the chat
Is
with
it
me.
gonna like spiral out?
Spiral source. Right. If it's complex, it's either a spiral source, a spiral sink, or a center. And the way you tell is by looking at the real part. If the real part's 0, it's a center. If it's positive, it's a source. If it's negative, it's a sink. Okay. So in this red plane, we're seeing a spiral source. Things are spiraling away from the origin on that plane. But things are spiraling, things are moving toward the origin along the green line. Okay. So now take a guess. What's going to happen? Just think to yourself for a minute. What's going to happen if I'm just near the green line? If you're near the green line, if I start with an initial condition way up here near the green line, I'm going to move toward the origin as if I were on the green line. But when I get closer and closer to that red plane, I'm going to spiral away. So what you'll tend to see is things that you see both the movement toward the origin and the spiraling movement at the same time. Give me 1 sec. I have to let my dog. Hold on. We have a guest instructor.
Oh my god.
How many dogs do you have?
I have 2. He's gonna make trouble. Sorry. All right. There's also teenagers running around this house somewhere, so I've got all kinds of challenges happening. I'm not sure which ones are more disruptive. Or where were we? Oh, we were up here. Right. I'm at this point way up here at top, and I'm going to move toward the this combined behavior of going toward the origin in a direction parallel to the green line. But also at the same time I'm moving toward the origin, I have to be spiraling away from the origin as if I were parallel to the red plane. So when you combine these, what happens is you see this curve that's going to kind of spiral around, and the spirals get bigger as I go more and more and more tangent to that plane. Okay, see if I could draw that better. So imagine now I just have this red plane, I have this green line, and things are moving around the red line, but the spirals are getting bigger and bigger and bigger as I go. Right, getting closer, and I'm going to keep spiraling out, and as I'm spiraling out, I'm going to get closer and closer and closer to that red plane without ever touching to the red plane, right? Because everything is asymptotic, just like before. What's wrong with my picture? Because I gotta. Now my OCD is going to kick in, and now I've got to, let's see what's happening. Oh, I see what happened. Is that clear?
Professor,
Yeah.
the vertical axis, was that like a third? That's the third eigenvector corresponding to -2.
Yeah.
So that's why it's going down, and then this plane is like the generating the spiral thing, and
Yeah.
that's because it's complex. I see.
Yeah. Yep. Yep. So in 2 dimensions, we have a spiral source, And then in this one other direction, linearly independent direction, we have a sink. And so this is, I mean, you could call it a spiral source saddle or something. I don't know what you want to call this thing. We're just going to use the term saddle as sort of a generic term. These things are moving away from the origin in one place, in one direction, and toward the origin in another direction. So we're just going to call this thing a saddle and not get too complicated about the names. But you should understand that there's some spiraling behavior here. Maybe it's more accurate to call this a spiral saddle or something like that. Yeah, Amber?
Do you mind scrolling up to the graph right above? So can you explain again how you got the red lines? Because of is the complex component just not part of the eigenvector?
Yeah, that's right. You just take the real and imaginary parts, and they give you two real eigenvectors. That's exactly right. Yeah. And if you go back to how we solve these systems, that's exactly what we did when we looked for the real solutions of these systems. Yeah. And we'll work through an example like that now. But other things, I'm not going to draw every possible picture. There are a finite number of pictures, but the possibilities are now much bigger. So I'll just, as an example, you could have, let's say you have 2 zero eigenvectors and a negative eigenvector. So in 2 dimensions, let's go back, just review 2 dimensions for a minute. In 2 dimensions, remember if we have a 0 eigenvector and a negative eigenvector, sorry. The 0 eigenvalue and a negative eigenvalue. The 0 eigenvalue corresponds to some eigenvector of fixed points, equilibrium points, right? And then the negative eigenvalue corresponds to some line where things are going toward the origin. And to fill in the rest of the picture here, everything just moves parallel to the blue line. Okay, so you can have the same sort of thing happening in 3 dimensions now. If we have, let's say, 2 zero eigenvalues and a negative eigenvalue. Okay, now you make a guess. Somebody tell me, what do you think the picture's going to look like?
Is it going to be like the same? Oh,
He's listening.
Is it going to be like the same thing, except now like the blue lines go like radially around?
Almost. Got 2 zero eigenvalues. So 2 zero eigenvalues could correspond to a 2-dimensional eigen.
So the red line's going to be a plane now,
Yeah.
and you're just going to have like the
Right. So these two 0 eigenvalues will correspond to a 2-dimensional eigenspace where everything is a fixed point. So we're in 3 dimensions now, and we have this plane, and everything on that plane is a fixed point. So imagine all these little dots on this plane, and they're not moving. As time progresses, they're just fixed. You still have this third axis where things are moving toward the origin. And now every other point also moves along a line parallel to the blue axis, and everything else is moving toward the red plane in 3 dimensions, just directly toward it. Okay, what about?
It'll have to be no.
Doesn't have to be orthogonal, no. Just parallel to the blue axis, whatever angle that axis is at. Yeah. What about, this one's a little bit harder to think about, a little challenge one. What if you have a 0 eigenvalue and let's do, thinking, let's do a complex conjugate pair. What do you think that looks like? Somebody else? Suresh has been answering a lot, like he always does, which is awesome. But I like giving everybody else a chance. What do you think happens there?
Maybe you have a plane that is the same as the plane we had before with like a spiral, and then you're gonna have another, and then you're gonna have a line
Yeah.
or like a vector of just every point on that line being a fixed point. I don't know how it looks like going towards the
Yeah. Now,
yeah.
now when you're off the, when you're, and before what we saw is when you're not on the plane of fixed points, you're parallel to the other stuff, right? So that's exactly what's going to happen down here. If you're not on this line of fixed stuff, you're parallel to the red stuff, which means all of space is going to get filled up now with these parallel red planes. And on every one of these planes, things are going to spiral away from the origin.
Okay.
Right, so there's no motion moving you off of one of those planes in the direction parallel to the blue direction, because the eigenvalue in the blue direction is 0. So in the blue direction, you're not moving toward the origin or away from the origin. Right, so if you have an eigenvalue of 0, it means that all of space is being filled up by a bunch of planes. And then what's happening on each of those planes is completely determined by the other 2 eigenvalues. So here's another quick example. Let's do 0 and a positive and a negative. So again, that just means that in the directions for 2, -2 and -3, you have some plane in space where you see a saddle behavior. The -3 and the 2 means you're pointing toward the origin and away from the origin. And things move along saddles in the other directions. Okay. And then there'll be this blue direction corresponding to the 0 eigenvector, where it's just a line of fixed points. And because things aren't moving away from the origin or toward the origin in the blue direction, it means everywhere else, you just see, no. You just see a plane that looks like it's parallel to the red plane, where you see these saddles on all the other directions. And so you have like a whole, and all of space is filled up by these saddle planes.
How do you know it's a saddle if you just have the 2, like if you know one is positive, one is negative?
Yeah, so the positive one is moving you toward away from the origin, the negative one is moving you toward the origin. And that's exactly our characterization of a saddle, is when things move away in one direction toward the other direction, it's a saddle. Yeah, good question. And then, I don't want to, it's 12:04, I do want to work through one example, one actual example algebraically, so you can see nothing really changes. But I encourage you now to just think of other combinations that we haven't done. What if you have 2 repeated eigenvalues? What if you have, I don't know, 2 repeated reals and a 0 eigenvalue or something? There's all kinds of other combinations that come up with other pictures. There's a finite number of combinations, but there's a lot of them, more than I can go through. But you should just have some sense that this is all that can happen. Let's just go through one real quick algebraically. They do a nice one in the book. So I'll go through it. Shouldn't take us long. It's 12:05, so we have 10 minutes. So let's do algebra for 5 minutes. Should be about all it takes. And then I want to spend 5 minutes talking about what happens in 4 dimensions, 5 dimensions, 6 dimensions, and higher. And again, there's nothing changes in those directions. You just can't draw pictures anymore because we don't have access to 4-dimensional brains that can see in 4 dimensions. All right, so let's see. The example they do is this one. It's nice. So here's the system. So it's the system 0.1000.2 and 0.400. Okay, and this is it's on page 361 of your books. You don't necessarily have to copy this down, but we can work through it. It does not take very long to go through. Wait, let me make sure this is actually the one they did. Hold on one sec. This was a nice one, but is this the one they did? Hold on 1 minute. There's one they had that was really nice. I think it was this one. Yeah, this was it. Okay, so we want to find the eigenvalues. So we're just going to go through the same algebra we've always done, right? We want to find the eigenvalues and eigenvectors. So to find the eigenvalues, you have to write down the characteristic polynomial. That means subtracting lambda from the diagonal and taking the determinant. Now, we haven't done a lot of determinants of 3x3 matrices. So let me remind you real quick how that works. So there's a couple different methods. So the method I like the best is not the easiest to remember, but it is the one that generalizes to higher dimensions better. So what I always do is I write down the top row with alternating sign. So here's the top row. We have minus lambda. Then we have 0.1, but I'm going to alternate the sign, and then 0. Okay, so I have positive minus lambda, negative 0.1, positive 0. Okay, again, I'm alternating the signs of those things. Right? And then what I'm going to see in each of those is going to get multiplied by something. And the thing that's getting multiplied by is the 2x2 matrix you get when you erase the row and column with that element. So if I erase the row and column with minus lambda, I'm left with this 2x2 matrix, and it's the determinant of that matrix that goes right there. Okay, so that's just, oops, I missed a negative sign, didn't I? Right there. So I get minus lambda times minus lambda is lambda squared minus 0. Okay, and then the next one is 0 times minus lambda minus 0.2 times 0.4, which is 0.08. Okay, and then the last one, doesn't matter what the last one is because I'm going to multiply it by 0, so I'm not going to bother with it. Doesn't matter. Okay, so all of this simplifies quite nicely to minus lambda cubed minus negative 0.1 times 0.8 is 0.008. Good. All right, now to solve that, I just set it equal to 0. And that turns into the equation lambda cubed equals 0.008. So I've got to find the cube root of 0.008. And now you may be very confused because you may say, oh, there's only one number whose cube is 0.008, and that's 0.2. 0.2 times 0.2 times 0.2 is 0.008, certainly. And it's really hard to think of a different number whose cube is 0.008. I don't want to spend a lot of time on this because we're not going to do it very much, but it's much better to think of this in the complex plane. In the complex plane, when you cube a point in the complex plane, what you're doing is you're multiplying its angle by 3, and then you're taking the cube root of its magnitude. So just a little tiny bit of complex geometry here. If I take a point in the complex plane, P, then when I cube that, if I want to graph P cubed, I have to triple this angle and cube the radius. And you can see that from writing P in polar form, r e to the I theta, then P cubed is going to be r e to the I theta cubed, which is r cubed e to the 3I theta. So the angle tripled and the radius cubed. Okay, so if I triple this and cube the radius, that's the point P cubed in the complex plane. Going the other way, you've got to think about where are the points that land you at 0.008. So if I want to end up at 0.008, I've got to think about where are the points where when I triple their angle, I end up at 0.008. 0.008 is a real number. It's over here somewhere in the real axis, 0.008. Okay. If I take the number 0.2, well, the angle there is 0. If I triple that angle, I end up with 0. And if I cube the distance to the origin, I get 0.008. I know I've shown this. Sorry, I have the relative magnitude. Instead of 0.008, let's just do 8. If I have 8, if I want the cube root of 8 in the complex plane, well, one of those points is just 2. That's the cube root of 8 is 2. But there's 2 other ones. There's this one and this one. This is 2 units away from the origin and an angle of 2 pi over 3. And then 2 units away from the origin and an angle of twice 2 pi over 3, 4 pi over 3. The thing about when you triple 2 pi over 3, 2 pi over 3, if I triple that, I just get 2 pi. So if I take this point right here, I triple its angle, now the angle is 2 pi, and I cube the radius, now the radius is 8, so I land right there. If you think of this point that's 2 units away from the origin, you triple its angle and cube its distance to the origin, you do end up right here. So this point is one of the cube roots of 8. And this point is another cube root of 8. If I have an angle of 4 pi over 3, if I triple that, I end up with an angle of 4 pi, which is also on the real axis. If I cube its radius, I get 8. Okay, all right. So all of that is just a long discussion. This has 3 cube roots. One is 2. One is 2e to the 2 pi over 3i. And the other is 2e to the 4 pi over 3i. Okay, now we can write that in real and imaginary form with Euler's formula. This is 2 times the cosine of 2 pi over 3 plus I times the sine of 2 pi over 3. Right, cosine plus I sine, that was Euler's formula. Cosine of 2 pi over 3 is, oh crap. I think it's 1/2. I think it's negative 1/2. I think that's square root of 3 over 2. Might have those flipped. I think that's right. So we end up with -1 plus root 3i. Now, these have to come in complex conjugates, so this one would have to be -1 minus root 3i. So 8 does have 3 cube roots. 2, oops, -1 plus or minus 3i. Those are the 3 cube roots of 8. So we were doing 0.008. It also has 3 cube roots. And they are, I'll just read them out of the book. It's the exact same procedure. It was 0.2 and minus 0.1 plus or minus I times the square root of 0.03. Very similar to what we got here up here. We just moved everything over by 2 decimal places. Okay, so in one direction we have
0.03 and not 0.3, because that one's moved over 2 decimal places rather than.
right, but when you take the square root of that, it's on the order of 1/10. Right.
Okay. Okay. Cool.
Yeah. Yeah. All right, so this means it's positive, so that means there'll be a line where things move away from the origin. And this means there's a plane where there's a spiral sink. You know, to figure out what plane that is, we would have to then look at the corresponding eigenvectors. You do that the same way. You just take your matrix, you multiply it by x, y, z. You'd set that equal to 0.1 minus 0.1 plus I times the square root of 0.03 times x, y, z. And I can tell you right now what they get. They got minus -1 plus I times the square root of 3 -2 minus I times 2 times square root of 3 and 4. We can rewrite that as -1 minus 2, 4 plus I times root 3 minus 2 root 3, 0.
I'm in class.
Okay. And then there's the real part and there's the imaginary part. So that's going to correspond to 2 lines in R3. Again, now if we plot those lines.
I didn't hear that. Tell me later. Wait, I want to laugh. Don't tell me.
Michelle, turn your mic off.
Oh, I'm so sorry.
Sorry.
This is my brother.
Correspond to these 2 lines. I'm not plotting them accurately, but we have 1 line and 2 lines. And in that plane spanned by those 2 lines, we're seeing a negative real part. So it's a spiral sink in that plane. And then you can also find the eigenvector corresponding to 0.2, which is positive. So then there's some other direction where it's a source. And they drew a better picture than I did. But they didn't. Actually, this one's got a pretty crummy picture, but I strongly encourage you to look at the book. Oh, well, you can sort of see it. Can you all still see my video screen? You see me like a little corner there? Okay, I'm gonna hold up the book and you can kind of see it right there. Right, there's this plane where there's a spiral happening, some spiral action happening, and then there's a line where things are moving directly away from the origin. Good. All right, shoot. That was supposed to take 5 minutes and it took 15 minutes. Damn it, and now I'm 5 minutes overtime. Let me just say real quick, give me 1 minute to just say what happens in 4 dimensions, 5 dimensions. Nothing new happens. The complex numbers are to come in complex pairs. The real numbers will just correspond to one at a time. And so in 4 dimensions, you could have 4 roots. Now you could have 2 pairs of complex things, 2 plus or minus 3i and 4 plus or minus I. That means there's a 2-dimensional plane in 4 dimensions where things are spiraling one way, and another 2-dimensional plane in 4 dimensions where things are spiraling a different way. Those 2 planes intersect at a single point, which is really, really hard to get your head around, how 2 different 2-dimensional planes in 4 dimensions can intersect at one point. But the idea is that you could still sort of understand at least what's happening on these planes individually. They're just, in this case, we would have spiral sources on these 2 different planes, and then things off of these 2 planes move in much more complicated ways. Even in 10 dimensions, if I'm in 10 dimensions, I could have a bunch of real eigenvalues, some complex eigenvalues, etc. And it just means you have all these axes with lines where things are moving toward the origin, away from the origin in 10 dimensions, and then a few planes where things are spiraling toward the origin, away from the origin, or just they're centers where they're just continually moving in circles around the origin. And that's it, right? There's no other behavior. It's just combinations of the 2-dimensional behavior we've seen. Things move toward the origin, away from the origin, or they spiral. And that's it. Quick questions before I let you go? Oh, homework. There are no web work problems on this stuff. So you want to just look at the book. Again, we're on section 3.8. And I would focus on problem 4 through 7. And let's see, so this is section 3.8. We're looking at numbers 4 through 7 and also 10 through 13. Again, these are just practice problems. They're just giving you 3-dimensional systems. You may have to go back and do some Wikipedia searching and just review how do you take the determinant of a 3x3 matrix if you don't remember how to do that. A lot of information on the internet out there. There's tons of like Khan Academy videos and Wikipedia pages. If that went by too fast. But everything else is the same. Finding the characteristic polynomial, once you know how to do a 3x3 determinant, that's the same. Setting up the algebra to finding the eigenvectors. Once you have the eigenvalues, that's the same. Everything else is just the same. You just have more equations and more unknowns. Okay? All right, good. I'll see you all on Wednesday.
Thank you.
Thank you.
Thank you, Professor.
Thank you.
Thank
Hi, guys.
you.